Welcome to Algorush. Today, we're going under the hood to see how data systems really work. From the apps on your phone to the services in the cloud, data systems are pretty much the invisible engines running our entire digital world. But have you ever stopped to wonder how they actually do it? How do they store billions of records, handle thousands of people all at once, and somehow never lose your data? Well, today, we're taking a journey deep inside these systems, starting from a single byte on a disk and going all the way to a globe-spanning network. Okay, so where do we even begin? Let's start with the most fundamental problem of all. If you have a mountain of data, how in the world do you store it so you can find one specific piece again, like instantly? Well, it all starts with this one simple idea, the page. Think of it like a standard-sized box. Instead of fumbling around with individual little items, the system organizes everything, your data, the indexes to find it, into these fixed-size pages. And that standardization right there is the secret to being fast and efficient. So you've got all these pages, all these boxes. Now what? You can't just scatter them randomly, right? They're organized into this incredible structure called a B-tree. It's basically a super smart, multi-level table of contents. The top page points you to the right section, which points you to a smaller section, and on until, boom, you land on the exact page with the exact piece of data you were looking for. It lets the system find anything in a massive data set with just a handful of jumps. It's amazing. All right, so we've got our data organized. We can find it super fast. Great. But what happens when someone trips over the power cord? How do you make sure that an operation that was only halfway done doesn't just corrupt everything forever? And just like that, everything's gone dark. The system's down, the data that was in the middle of being written is now in some weird, unknown state. This right here is one of the absolute most critical problems a data system has to solve, guaranteeing that your data will survive no matter what. The solution is actually kind of brilliant in its simplicity. It's called the write-ahead log, or WAL for short. Before the system even touches a data page, it first jots down a quick note in this log. It's like a captain's log, right? I'm about to change this record to this new value. That note gets securely written to disk first. So when the power comes back on, the system has this trusty log. It doesn't even bother looking at the potentially messy data files at first. Instead, it kicks off this really cool three-step recovery process. First, it reads the log to figure out exactly what was happening. Then, it replays all the completed notes to get the database back to where it was supposed to be. And finally, it finds any notes about things that never finished, and it just undoes them, leaving the database perfectly clean and consistent. All right, so we're leveling up here. We have a system that can store data and survive a crash, but real-world systems aren't dealing with just one person, are they? They've got thousands of users, all trying to read and write to the same data at the exact same time. How do you stop that from becoming pure chaos? This is where things get really messy, right? If two people try to update the same account balance at the same time, who wins? What happens if you're trying to read a report, but someone else is changing the numbers right under your nose? You can end up with all sorts of bizarre, corrupted data. So, how do you prevent this chaos? Well, there are a few different philosophies. One approach is to be, pessimistic. You assume things are going to go wrong, so you use locks to control access and prevent conflicts before they even happen. A classic tool for this is a reader's writer lock. On the other hand, you could be optimistic. You just let everyone do their thing and only check for conflicts at the very end. And a lot of modern systems use this really clever optimistic trick called multi-versioning, where readers see a consistent snapshot of the data so they never get in the writer's way at all. But for now, just to get the main idea, let's look at that pessimistic lock. Its rules are simple but really powerful. And here are the rules of the road. It's actually pretty intuitive when you think about it. Any number of readers can look at the same data at the same time. No problem, they're not changing anything. But the moment a writer comes along, they need exclusive access, total control. No one else is allowed in. And this makes it crystal clear, doesn't it? On the left, you've got multiple readers all accessing the data together. No problem. But look on the right. As soon as a writer gets the lock, it's like putting up a giant do not enter sign. Every other operation, whether it's a read or another write, has to get in line and wait. Okay, so we've built a pretty robust single machine. It's got rules for storage, recovery, and concurrency. It's solid. But what happens when that's just not enough? When your data gets too big or the traffic gets too high for just one computer to handle, you have to scale out. This is where we enter a whole new world of problems. And there's this famous quote that just perfectly captures the kind of paranoia you need in this world. It says, a distributed system is one where a computer you didn't even know existed can fail, and suddenly your own computer stops working. In this networked world, you're suddenly forced to make an impossible choice. It's famously known as the CAP theorem. And the deal is this: when the network breaks, when parts of your system can't talk to each other, you can't have both perfect consistency and perfect availability. You have to pick one. A bank, for instance, is going to choose consistency every time, but a social media site might choose availability because showing you slightly old data is better than showing you an error page. You have to choose. So this all builds up to what is, honestly, the final boss of data systems. If you have a cluster of machines separated by a network you can't trust, how on earth do they agree on, well, anything? How do they agree on what the correct data is, or even who's in charge? This problem is formally known as consensus, and it is the absolute bedrock of almost every single reliable distributed system out there. It's basically a protocol that lets a group of machines all vote on a value and agree on a single outcome, even if some of them crash or their messages get lost along the way. Now, for any consensus algorithm to actually be considered correct, it has to satisfy these three non-negotiable rules. Agreement: everybody who decides on the same thing. Validity: they can't just invent an answer, it has to be a value someone actually proposed. And termination: sooner or later, they have to actually make a decision. For decades, the main algorithm for this was famously, notoriously difficult to understand. But in recent years, new algorithms like Raft came along with a revolutionary goal: to actually be understandable. And this has made it possible for way more engineers to build these incredibly reliable systems.
So after all that, B-trees, logs, locks, theorems, why does any of this really matter? Because without it, almost nothing in our digital lives would work. Period. Every time you make a financial transaction, systems have to reach a consensus on your new balance. Every time a big web service updates its configuration, all of its thousands of servers have to agree on the new settings. Without consensus, it would all be unreliable chaos.
So we've gone from a single page on a disk all the way to global consensus. These are the fundamental building blocks of the world we live in. But as our systems get even bigger and even more complex, the fundamental challenge of getting them all to agree on a single source of truth